Hi, it's Ian Shapiro, and I'm here just to go over a typical heat pump outdoor unit. This is made by Samsung, and we see a heat exchanger on the side. That heat exchanger wraps around the back, and that heat exchanger is what helps the heat pump do its thing. In the summertime, it's rejecting heat to the outdoor air. In the wintertime, it's absorbing heat. This unit is actually running, and the whole heat pump outdoor unit, fans, heat exchanger, and in here, compressor and controls. Now what we've been examining is what we call air bypass. It's the movement of air around the heat exchanger. We want all the air to move through the heat exchanger, but what we've discovered is that some air, in fact a measurable fraction, bypasses. And we'll show you some of those bypass locations.
Before we show you all the different bypass locations, first we'd like to familiarize ourselves with typical side flow outdoor heat pump unit. What you see in front of you now is an exploded view of one of those typical units, and then this analysis we will take 12 different components of this unit into consideration.
In the control compartment, not a lot of air is supposed to flow through, but we have seen some places where that's possible to have some air bypass. It's like this one hole here. The air can simply be sucked through this hole into the fan section. Where that can come from these stamps, which the contractor can push out, like what Ian said, and these purposeful ventilation vents. Right. And all of these are going to add to the air bypass ratio, which may be purposeful to cool down the electronic section, or it might not be, and it will hurt the efficiency of the heat pump.
Well, this is the heat exchanger. The largest air bypass was at this end. There is no tube sheet. There's a tiny tube sheet here, which is a piece of steel anchoring the end of the heat exchanger, but it's not fastened to this side panel. So air gets in right up through here, and we measured about 1/4 of an inch gap all the way down, over 50 inches. And it gets in through here and goes through the fan. The second biggest area of bypass was over the top of the coil. We've got this fan motor bracket and we've got these spacers, but this is about 1/4 inch to 3/8 of an inch of total gap. The air comes over the top and into the fan. We had also air bypass at the bottom of the coil underneath it, and that was measurable. We've identified the biggest air bypasses so far in this fan section. The final general area of air bypass is from the outdoors into the control and compressor compartment at the end, and then from there into the fan section. And that turned out to be fairly substantial. And we will point out where it goes. Probably the biggest bypass from the control compartment into the fan section is this heat sink, and it is a vent to cool the electronics. There's a heat sink back there cooling the electronics, and they're letting outdoor air into this control compartment and then into the fan section without going through the heat exchanger. If we reduced that air bypass, more air would go through the heat exchanger. We would be raising the efficiency of the whole system.
Here, you now join me underneath the heat pump at the base pan. This is where we're going to see a lot of the condensate drain holes. And we did see them in action today when we're running the heat pump in cooling, where water would condensate and drip out from these holes. These are also pretty good bypass sites, pretty significant bypass sites. And as you can see, there is quite a lot of them underneath this heat pump. And after sealing them, we reduced the CFM by around 30 CFM after sealing all of these holes.
We're looking at the base pan, specifically the gap between the coil and the base pan of the Samsung unit, which is a bypass site. Here is the fan clip holes, which is another bypass site. Here is the long end. You can see the gap where it's circled. That's where air can bypass into the control compartment. This is the pipe and wire penetration holes, which is a pretty substantial bypass site in this unit. And here we measured the coil gap by squishing some putties and measuring how thick the putty is, which will show how much of a gap there is between the top cover and the coils.
Hi, this is Maheshwar. I'm a PhD student in the Department of Mechanical and Aerospace Engineering at Syracuse University, and currently I'm in 4th year. So in order to quantify, we do the characterization, and for characterization we basically use the visual inspections. With the smoke test also we visualize on the air bypass flow. The most important is to do the measurement of the air bypass in order to quantify it. Talking about the solution, like how we can reduce the air bypass, we can use the sealing tools. For example, we can use the weather stripping or the foam here. For the drain holes, we can ask the manufacturer to make the smaller size drain holes, or the use of any valves which helps them to allow the water to pass down but block the airflow from the outside to the inside through the drainage hole.
There are lots of seams on these heat pumps which we can't exactly measure with a tape measure, so we use something called a feeler gauge, where they are just metal sheets that differ in thickness and they go in order. So how you use it is you pick a width. This is 0.4 millimeters, and you pop it in the hole, and if it fits, it means that it's either that thickness or it's bigger than that. So then you go the next size up, and you repeat those sections until you are not able to fit the gauge in anymore, and then you go back down to the last size, and that's the size of your gap. So some of the gaps though are notably much bigger than other ones, so we have to use wooden shims to kind of make our own bigger feeler gauge. These are tapered at an angle, so we are able to insert it until it stops and then measure with a pair of calipers. So for an instance where we have a big gap right here, like we've talked about before, we're able to insert it, so then we're gonna get the amount that it's thick.
The next sequence of videos will be shown is the smoke tests. In order to do the smoke test, firstly we need to block the heat exchangers. This shaded area of this heat pump is the heat exchangers, and we will be blocking them with saran wrap. And by completely blocking the heat exchangers, we will stop air from flowing through them, which will highlight any bypass sites the heat pump will have. Now, what we're looking at is the base pan of the Samsung. We're looking at the back part of the heat exchanger, and looking to the right of your screen, you will see some smoke that flows underneath the heat exchangers right there. Now this highlights the bypass sites flow underneath the coil. Now looking to the left of your screen, we're going to show that it also happens towards the left of the screen as well, which further shows that the Samsung unit has a lot of bypass underneath the coil. Now looking at the top of the Samsung unit, we will see some smoke coming up above the heat exchangers to the right of your screen. Now this also shows the lack of gasketing on the top cover. Now in this Daikin unit, we're looking at the short end of the coil, which is one of the most substantial bypass sites of our heat pumps here. And see, there's a lot of smoke pouring in from that short end. And in the next video, in the Daikin unit, we can see how air flows bypass the coil from the outside in. You can see it goes into those gaps, which flows around the heat exchangers. Now in this research, we have collected data on 4 main heat pumps, being the Mitsubishi, the Daikin, the Samsung, and the LG, all of which have been installed in the last 5 years except for the Daikin, which is an older unit. Now other HVAC units that we have used in this research for characterization are the Lennox, the Tadiran, the Goodman, the Fujitsu, and the Bosch, with the Lennox being an AC only unit. As for the results of our tests, we can see that there are some discrepancies between the characterization calculations and the measured block coil tests. We can see that Samsung has very close bypass percentages between the two methods, and the Daikin has overall the lowest amount of bypass. Now drawing your attention to the temperature mixing methods, we can see the 3 heat pumps that are highlighted in green. These are unusable data. This is because sunlight that has shined on the probes affects the temperature reading.